All right, so now let's talk about this particular question. So in this question, we are given a sorted array of distinct elements, right? And when we say sorted array, it is sorted in increasing order, right? You can just take it like that. And what the question is also saying that this sorted array is also rotated at some unknown point, right? And our task is to find the minimum element in this sorted and rotated array, right? So that's what we need to do. Now, for example, if you see this particular input array 5, 6, 1, 2, 3, 4, right? So now the output should be 1, right? Because the minimum element in this sorted and rotated array is 1. And how it is sorted and rotated? Because if you see, the original array would have been 1, 2, 3, 4, 5, 6, right? And then 5, it would have been like right rotated, and 5, 6 would have come over here. So now after doing that rotation, it would have become 5, 6, 1, 2, 3, 4, right? And that's how it is sorted and then rotated. And the minimum element in this sorted and rotated array is 1, right? So that's what we need to figure out. We need to find the minimum element in this sorted and rotated array. You can just pause this video here and try to think of a solution. And once you are done, you can just come back and check the solution here. Okay, so now to solve this particular question, see, one very basic observation that we have to keep in our mind is that the minimum element in this sorted and rotated array, or any sorted and rotated array, would be actually the the element from where the rotation actually starts, right? So what I mean to say is, I mean, you can also think of it this way, that wherever the increasing order of the numbers are actually violated, that would be the minimum element, right? For example, the sorting order is increasing over here, right? So now this is 1, 2, 3, 4, right? This is 5, 6. But if you see between these two elements, the sorting order is not increasing, right? It is 6 and 1, so it is decreasing. So over here, the sorting order is violated, and that's where, we will have our minimum element, right? We will always have our minimum element at the point from where the rotation starts, or you can take it otherwise, like wherever the sorting order between the two elements is violated, we have to take the second element between those two elements as the minimum, right? And that will always be the case, right? So you can just consider it like this. If I just write the original array over here, right, it would have been, just give me a minute, 1, 2, 3, 4, 5, and 6, right? Now this is the original array, and after rotation, the 5, 6 came over here, 5, 6, and then 1, 2, 3, 4, right? So 5, 6 actually got appended before the minimum element, right? Because the first element would be the minimum element in any sorted array, right? And when we are actually rotating any array, we are actually either appending the larger elements before the first element, or what we are doing is we are, actually appending the minimum elements, like the first elements, after the last elements, after the greater elements, right? But in either of the cases, the minimum element will always be after the larger element, right? It will be at the point of the rotation, right? So all what I need to do is to find the minimum element, I just need to find this point of rotation, right? I just need to find those two elements, right, which are violating the sorting order, the increasing sorting order, right? That's what I need to figure out. That's my primary observation over here, right? But how do I do that? Now what I can do is I can apply binary search to achieve that, right? So what I can do is I can keep dividing this original input array into two halves, right? And I can always keep moving towards the array which is not sorted, right? So like when I actually divide this particular array, input array initially, this will be my mid, right? So if you see, all the elements from mid till the last of this particular array are sorted, right? But from the first element till the mid are not sorted, right? So then I will move my binary search to the left half, right? Because see, the first half, like the second half, the right half is already sorted, right? But my minimum element, as we discussed, would be in the non-sorted part, right? Where the sorting order is actually violated. That means it is non-sorted, right? So that's why I will just keep moving always towards the not sorted, like the unsorted half of the input array. And I will again do the same thing. I will again apply binary search over there. And again, I will move towards the non-sorted part of the non-sorted half of the array, right? And I will keep doing this till I actually come down to just one element, right? Till I am left with only one element, and that is going to be my minimum element, right? Because I have applied binary search on, all the possibilities now, and I have always kept moving towards the non-sorted part, non-sorted half of the array. And after once I am left with just one element, that is going to be my minimum element, right? So that's the approach that I'm going to follow. That's how I'm going to utilize, binary search over here to do this efficiently. And now if you talk about the time complexity also over here, I mean, it will be order of log n because I'm just applying binary search over here. So it's like a customized version of a binary search. My stopping condition is a little different, but then at the end of the day, it is binary search, and I'm just, dividing, the entire array into two halves every time. And that's why the time complexity over here will be order of log n, right? So that's the entire approach. I hope you understood it well. If not, maybe you can just follow along the code and that will give you a better understanding. So let's jump to our IDE now. All right, so now let's implement the solution that we discussed. So now let me just declare a function. I can call it as find min, right? And this will accept an integer array, right? Now what I can do is I can just capture the length of this particular array in a variable n, right? And then I can just declare my left pointer for the binary search and initialize it to 0, and also my right pointer and initialize it to n minus 1. That is the last element of the array, right? And now what I can do is I can run a while loop over here. I can say while l is less than r, right? And now what I will do is I will just keep finding mid over here in every iteration by l plus r divided by 2, right? And now what I will do is I will check. Now see, what I need to do is I need to figure out which half of my array is actually sorted and which half is unsorted, right? And then I have to move towards the unsorted array and then again apply binary search over there, right? So now my objective is that I need to find the unsorted part of the array, right? And for doing that, what I can actually do is I can compare my current element at mid, right, with the last element, right, of the array. That is the right pointer, right? So if my current element at the mid pointer is greater than my current element at the right pointer, it would mean that the right half is actually unsorted, right? Because see, essentially, if it would have been sorted, if the right half would have been sorted, then my mid element would have been lesser than my right pointer element, right? Because see, we are saying that the array is sorted in the increasing order, right? And mid is appearing before the right pointer. So obviously the element at the mid pointer should be lesser than my right pointer if this right half was to be a sorted array, right? But then if it is greater than the right pointer, the element at the right pointer, we can say that the right half of the array is actually unsorted, right? And the left half is sorted, right? And so I need to now apply binary search. Sorry about that. Yeah, I need to apply binary search on the right half now, right? Because as we discussed, we know for a fact the minimum element would always be present in the unsorted part of the input array or the overall array on which we are applying the binary search, right? So that's why we will now apply the binary search on the right half. And for that, I will just, do L equal to mid plus 1, right? And I will move to the right half, right? And if this is not the case, if, my array of mid is actually lesser than my array of right pointer, it would mean that the right half is already sorted, right? It is following the order which it should, right? And that would mean that the unsorted part would be the left one, right? Because from both the parts, at least one has to be unsorted, right? Only then it will be rotated. That's the beauty. I mean, if you have rotated a sorted array and if you break that, like divide the entire array into two parts, for sure, one of the part will always be unsorted, right? Because, the array has been rotated. So now that's why if this is not true, if the right half is actually sorted, then we can safely say that the left half is unsorted, and now we have to apply the binary search on the left half, right? And so now I will do r equal to mid, and I will not do mid minus 1. I just wrote it just to make it clear. We are not going to do r equal to mid minus 1. Over here, we are going to do r equal to mid. And why we would be doing r equal to mid? Because see, we are saying that all the elements from mid, right, starting from mid till the last element are in the sorted order, right? They are sorted in the increasing order, right? Which would mean that even mid could be the minimum element, right? And it would be the minimum element if the element right before the current mid is actually greater than mid, right? In that case, we can say that the sorted part of the array actually starts from, mid itself, right? And in that case, mid will be the minimum element, right? So like I don't mean to confuse you, but then since we are saying, since we have concluded that, array of mid is actually lesser than array of R, it would mean that all the elements right from mid, right? And not like mid plus one, right from mid, all the elements till the last element of the current like array that we are applying binary search on are all sorted. It would mean that even mid could be the minimum element, right? And that's why we have to include mid while doing the binary search on the left half of the array, right? And that's why we will do R equal to mid and not mid minus one, right? So that's why there is a small customization over here. And now once we come out of this while loop, once our L becomes equal to R, right? That means this particular condition will now get violated and we will be left with only one element now, right? And now that one element, that last element would be actually the minimum element of this particular array, or it would also mean that that particular element would be the element from where the rotation starts, right? And that would be the minimum element which we have to return, right? So after coming out of this while loop, I can just say return array of L, right? And I can also say return array of R, right? Because L will be equal to R over here now, right? Because that's where the condition got violated and we came out of the while loop. So I can either return array of L or I can return array of R. It would mean the same thing, but just for the sake of clarity, I can say return array of L, right? And that would be my minimum element, right? So this is the entire algorithm. I hope you understood it well, why we are actually how we are actually applying binary search over here and making use of the fact that if my current element at the mid is actually greater than the right element, it would mean that the right half is unsorted and then I will have to do binary search on the right half, and otherwise I will have to do it on the left part of the array, right? So that's how we are going to solve this particular question. Talking about the time complexity, as we discussed, it is going to be order of log n, right? And since we are not using any extra space over here, it is going to be constant. It will be order of 1, right? So now this is all about this particular question, and I will see you in the next one. Thank you.